Hello everyone, welcome you all to the new lecture series in the title State Space Analysis. So in this video, we will introducing one of the most foundational topics in modern control system, which is a state space representation and transfer function conversion. I hope this lecture will help you to grasp the key concepts of state space analysis in step by step. Let me explain it with the help of upcoming slides. In the first slide, we are going to discuss about the state space representation. So state space is a powerful way to represent physical system mathematically. Unlike classical control, which uses higher order differential equations, the state space makes break it down into first order differential equations. This makes the analysis more organized and scalable, especially for the system with multiple inputs and multiple outputs, which we are naming it as a MIMO system. One major advantage is that it's highly suitable for modeling multivariable systems, making it ideal for real-world engineering problems. And in the next slide, we are going to discuss about the state variables. So what are the state variables? They are small set of variables that describes the complete internal state of a system at any time t. We denote them as x of t. For example, the current through the inductor or voltage across the capacitors, which we are considering it for the state variables. We write them in the vector form, which is x of t is equal to x1 of t, x2 of t. It will extend up to xn of t with the transpose T. This forms the basics of all state modeling and are essential to track the behavior of dynamic states. Next, we are going to deal with the state model, which is the state equations along with the output equations. The state model consists of two basic key equations, which is state equation and output equation. In the state equations, we are going to see about x dot of t, which is equal to ax of t plus bu of t. In the output equation, we are going to see about y of t, which is equal to cx of t plus d into u of t. And we have the A, B, C, D matrix as A is the system matrix, B is the input matrix, and C is the output matrix, where D is the feed forward matrix or direct transmission matrix. Together, they define the complete system behavior in the matrix form. Next, we are going to see about the solutions for the state equations. To analyze a system, we need to solve these state equations. They are in the two parts of homogeneous solution as well as non-homogeneous solution. In the homogeneous solution, we can see about it x of t, which is equal to e power at multiplied with x of 0, which describes the system behavior with no inputs, and deals with the non-homogeneous solutions, which has x of t, which is equal to e power at multiplied with x of t, adding with integral of 0 to t e power a into t minus t b u of t, which is multiplied with dt. This includes the effect of external input, which is u of t. The key here is the matrix exponential, which is e power at, which tells us how the system evolves over the time period. And now we are going to see about how to compute this matrix exponential. We can do this by means of three methods. One is series expansions, Laplace transform, and diagonalization. In series expansions, uses the infinite sum of matrix powers. In Laplace transform, we are going to deal with the conversion, which converts the time domain equations into algebraic S-domain equations. And in the normalization, if a matrix A is diagonizable, this method simplifies the computing dramatically. Each technique is chosen based on the nature of the system. And now we are going to see about state space to transfer function conversion. So let's link this state space to something more familiar, which we are naming it as a transfer function. So the conversion formula is g of s, which is equal to c into si minus a, the whole inverse multiplied with b plus d. This gives the system input-output relation in the Laplace domain procedures. And we have certain procedures that we are going to discuss now, which is compute inverse of Si minus A, take its inverse, then we have multiplied it with B, then multiply with C, finally add all this component with the D. This helps bridges the gap between classical and modern techniques. So let me conclude this by state space modeling gives us a structured way to represent and to solve the complex dynamic systems. By mastering how to convert it to the transfer function, you gain the flexibility to apply both the classical as well as the modern analysis tool. I hope you have understand this video. Let me introduce some other topics in the upcoming video. Thank you.